Good day, friends. Today we're going to continue our optics course, and today we're going to discuss about the particle nature of light. As usual, I love to repeat that light is, by its nature, an electromagnetic wave, and the ray nature of light is not actual nature of it, but the mathematical abstraction. However, as this idea was proven by Thomas Young's double-slit experiment, and after it was proven by James Clerk Maxwell mathematically, after some time, being exact, about at 1900s, the man called Max Planck had supposed that light spreads in discrete packets. Why it was a problem? Because before it was said that it consistently spreads energy not in packets but as a waves, right? But right now, Max Planck has supposed something new, that light has discrete packets of energy, and he called them quanta, and later these discrete packets appeared to be small particles, and then it was called photons. Okay, those photons had no any mass, they had momentum and energy. Interesting fact from physics is that there is a rule that if you have any mass, you cannot move at speed of light. So if you have a mass, the speed of light is unachievable. However, if you are massless, then you have to move only at speed of light. So that's what makes light have no mass, right? Okay, good. However, there is a problem about Planck's idea, because he did not believe it himself. He supposed that it has discrete packets of energy, photons. However, the problem about it was that he still believed this wave nature of light because it was proven by Thomas Young and James Clerk Maxwell. However, Planck supposed that this still works, his idea still works, but he said that it is also mathematical abstraction, just like the ray nature of light. So ray nature is not the nature, but its ability. It also, Planck supposed that it's not the actual nature of light being a particle, but instead it's an ability, just ability, one of its abilities to spread energy in discrete packets. Okay, each of those discrete packets had such kind of value. It is the Max Planck's constant, which is written right here. It's 6.6, 10 to the power of minus 34 joules second. This is the smallest packet amount of energy that is possible in the nature. Okay. And the frequency of that electromagnetic wave, or better to say, the photon. Also, we know that frequency has its own formula, which is c divided by lambda, and that's why we can write it in two kind of forms, that each of those discrete packets have an energy, the amount of which is equal to Max Planck's constant multiplied its frequency, or Max Planck's constant multiplied speed of light divided by wavelengths of that wave or the photon, right? Okay. Even though Max Planck did not believe this his idea himself, after some time, in 1905, Albert Einstein came up with the theory called photoelectric effect. So what is a photoelectric effect? It does not have to do anything with photo, it is instead photon, This word here we have photon. So, and electric, it is not exactly about some electricity or something, it is this part, electron, This is electron. So, right now we understand that this has to do something with photons, and electrons. And the exact definition of photoelectric effect is emission of electrons from a material surface when light of sufficient energy shines on it. So maybe you don't understand it, but let's try to make it easier. So it goes like this. This formula to you might seem not much familiar. Maybe you have studied it. If you did, it's good. But let me try to translate the formula language to the basic life language. Okay. So it goes like this. The energy of photon, when the energy of photon is sufficient, that is said in here, if it is enough to knock out some electron, work function, this thing, work function, then it gains some kinetic energy. So first let's start from this thing, we have already discussed it in fact, but let's go back to it and talk about it again. So this formula is exactly that formula, This energy of photon is exactly this thing. It comes from the energy of the photon from Planck's theory, So it's energy of the individual photon. Sometimes photons might have high energy, sometimes lower energy. That's why sometimes energy of photon might be insufficient. Sometimes it might be enough to knock out the electron. What about the work function? Work function, it's a property of a material. It's a minimum energy required to pull electron out of material. In other words, it is how strong are electrons bound to the atom. So it is the scale, maybe we can call it maybe a scale, or some factor which shows how much some electron is tied to its atom, right? And it also might depend on different kind of factors as energy levels and so on and so on. However, let's not complicate it. You just understand it just the way I have explained to you just right now, okay? And if this energy appears to be more than it, of course, this energy goes to what? The energy of it goes to kinetic energy of the electron. Because if you win from that energy, minimum energy that is bound to the atom, then of course this, when you split this electron from it, it goes somewhere. It gains some velocity and it gains some kinetic energy. Yeah, we can open up this formula just like the HF. Work function just stays like a work function, and kinetic energy can be opened up as its usual formula, mv squared divided by 2. Okay, in the form of the diagram, it would look something like this. Yeah, this thing doesn't have to be metal bar all the time, but mostly and usually we work with metal bars because they are electrons. It has a lot of free electrons. Yeah. Okay. So what these lines are is the direction of photons which approach the metal bar, like this one. Yeah. The photons, they have some energy which is hc divided by lambda. We have discussed it already. Yeah. If we go inside of the metal bar, of course we know that all of them are just a combination of many atoms. Yeah. So we have this kind of one atom. Yeah. Let's consider just one atom. We have a photon which approaches with some energy which is hc divided by lambda, and then we have, for example, this electron. Let's take this electron which is bound to its atom with certain work function, and when it hits, yeah, this electron, photon gets completely absorbed. This is a very important moment. We need to write it here. Photons get completely absorbed. This is a very important thing, to be completely absorbed, because if it is not, it becomes something else. And we're going to talk about it a little bit later, okay? When this photon gets absorbed, of course, it wins the work function, and also it moves electron with some velocity, and it gains some kinetic energy instead. Of course, electrons have some mass, and they gain some velocity. And divided by 2, you know all this thing. Okay, good. I hope it was clear to you. So let's move to the next law, which is Compton effect, yeah? Let's talk about the Compton effect. Compton effect has a little bit, maybe a little bit less intuitive, but still not that hard formula. The Compton effect has such formula, which is delta lambda, the difference in wavelengths, equals to Max Planck's constant, mass of the electron, and speed of light, inside of the brackets 1 minus cosine theta. Okay, yeah, you can see it. Okay, let's discuss about this formula a little bit more in detail. First of all, what is that difference in wavelengths? We have some scatter wavelengths, we have some entering wavelengths, yeah, we have Planck's constant, as I have said, mass of the electron, speed of light. By the way, all of these three factors are constants, yeah, right? These are all just constant numbers, they do not change, but the only thing that changes is this theta, yeah, the angle of scattering. Okay, what is going on? What is scattering? What is going on? What is happening here? Okay, let's say something like this. This image, or let's go to this image, yeah? It's not the same image as before because it's here, this one, yeah, metal bar. This one is different, a little bit different. Look at this. We have also something, yeah, it does not have to be metal again. As I have said, this thing does not have to be metal all the time. It can be something else, but mostly we work with metal bars. Here it does not matter much, yeah. Okay, here again we have some photons approaching like this one. They have some sufficient energy to knock out the electron. Electrons go some direction maybe with kinetic energy. However, this photon does not get completely absorbed. No, instead it has some energy left. And this energy goes in the form of longer wavelengths, hc divided by lambda 2. Yeah, you might think, yeah, this thing is a little bit strange because at the beginning we have something very short wavelengths, and then this wavelength becomes bigger. Do you mean something like energy increased? No, energy did not increase. In fact, it decreased. Why? Because you had some initial energy here, then it split it up into two. One of them is kinetic energy, the second one is this one. But why this wavelength got longer? Because we know that by energy of photon, it is positively proportional to the frequency. However, it is negatively proportional to the wavelengths. So higher the wavelengths, the less is the energy. So it's exactly that thing. Lambda got larger, however, energy decreased as we expect it to be, because some of the energy right now is in kinetic energy, right? Okay, good. I hope you understand it. Something very close to the photoelectric effect, yeah? But instead of getting completely absorbed, it gets partially absorbed, yeah? And some of its part that did not get absorbed, they just go as photons of less energy. Yeah, okay, good. In the form of diagram, it would look like this. For example, if we choose some axis, yeah, if we choose some axis, it's completely the same thing, but I want to show you what is about that theta. I have told you that only thing that changes here, all three are constants. However, only thing that changes is this one. And what is that theta? For example, if we draw some hypothetical axes, yeah, y and x, then we have, for example, at the center of that some electron. Okay, when photon comes here, and after it knocks out this electron, it goes some direction of the angle called theta, and that is exactly that theta which is in the formula. And it goes different direction. Also, it gets longer wavelengths, as it was mentioned right here. The frequency, we know that lambda and frequency are negatively proportional to each other. So if lambda rises, frequency falls, and energy also falls. And at the very beginning, as you can see, wavelength is shorter, frequency is higher, because aligns at the very same amount of time, as you can see, for example, this time, and let me draw almost the same, for example, this one and this one, they look almost the same length, but in this fraction of time, like time and time, these waves repeat more frequent than this one, as you can see, okay? Yeah, frequency is higher, energy is higher, and it's logical because some of the energy went to what? Went to electron. Electron gained some kinetic energy, okay? Good. Yeah, good, I like it. So, what about this angle? Maybe it's some alpha, maybe it's some beta, it does not matter. But in fact, we are not interested on this thing because in the formula, we are not interested much on the electron. Only thing that is important about electron is mass, because it hits the electron, and electron just plays the form of some sort of a obstacle, let's say, yeah. But we're interested in the last result, which are our initial wavelengths and the last wavelengths of our photons at the very beginning and energy of the photon at the very end. That's why we're interested only on this angle, which is theta, but we're not much interested on these angles, which may be just alpha, beta, or anything, because we don't concentrate on electron, we concentrate on photon. Yep. Okay, let's go back to this one. Yeah, I was meant to tell you about this at the very beginning, but it's still not late. As you can see, let's discuss about this. In the form of waves, you can see that the longest wavelengths, like this one, yeah, radio waves, microwaves, infrared, they have low frequency, as you can see. Yep. They have some low frequency. That's why those they have a high lambda. Yeah, they have very high wavelengths. They have low frequency. That's why they have low energy. Okay. So what about next one? The visible light. It's the spectrum that we see. Yeah, that allows us to see anything, colors or any light, any shadow. We see only on this spectrum. So these all are electromagnetic radiation spectrum, right? But only this spectrum allows us to see anything. Okay, we don't see this part, we don't see this part and this part. We cannot see microwaves or infrared, but we definitely can see naturally visible light. Yep. Ultraviolet, as you can see, its wavelength gets shorter, its frequency gets higher. That's why its energy is also higher. And when we go further, like X-rays and gamma rays, their frequency, as you can see, it's very high. Its frequency is very high. That's why their energy is the highest. That's why gamma rays, they are very dangerous because they used in medicine for killing cancer cells, of course. Okay, yeah. Gamma rays, they are dangerous, in fact. Yep. Okay. Low energy, as you can see, yeah, because high lambda and low frequency, and here it is higher energy because the frequency is high and wavelength is short. Okay. Good. And let me explain that photoelectric effect usually, yeah, normally works in small energy area like visible light, maybe some infrared, yeah, like this, maybe some microwaves, radio waves, and something like that, yeah. Mostly energy here in photoelectric effect, it's low, but mostly it can work in higher energies, it's okay. And normally Compton effect operates in higher energy, yeah. It operates in higher energy. It can also appear in lower energy, might be, but mostly, usually, we work with Compton effect at high energies. Okay, good. Let's continue. Yep. So let's head back to this formula. As you can see, we have initial wavelengths, which is definitely shorter because energy is high, and last wavelength, which is definitely higher because energy is lower. Yeah. Okay. So that's why this thing, our last lambda, this is last lambda, which was scattered, yeah, it must be first because it's larger, and the second one is lower, the initial wavelengths. I hope now you understand this initial wavelengths, lambda 0, is this part, which is entering the atom, and the second one, which is scattered wavelengths, is this wavelengths. Okay, good. And as you can see, if this is lambda 2, if this is lambda 1, then definitely lambda 2 has to be larger than lambda 1. Why? Because its frequencies have to be, instead, frequency 1 has to be larger than frequency 2, which means that energy at the very beginning has to be larger than energy at the very end. And it's pretty much logical, okay? Something very important to say, that as this electron gains some kinetic energy, as you can see it just right here. If you looked closely, then you can see here we write it mv squared divided by 2 in photoelectric effect, but we cannot write it mv squared divided by 2 right here. Why? Because this thing will not be equal to usual mv squared divided by 2 because it operates in high energies, as I have told you, it kicks the electron. Instead of being completely absorbed, photon just kicks it, wastes some energy on the electron, and it goes almost at the speed of light. It is relativistic speed. That's why we cannot use just classical energy formula. Yeah, but we definitely can say that it is the difference between initial energy and final energy. Yeah, because due to conservation of energy, it works at any scale all the time. Conservation of energy. Then energy at the very beginning is only the initial energy of the photon, and then it splits into two halves. One of them is kinetic energy of the photon electron, and it is also the final energy of that photon. And when we throw it here, then definitely energy initial minus energy final, which is definitely this thing. Okay, yeah, we can open both of them as hc divided by lambda, but this thing would be lambda 1, this thing would be lambda 2. And when we take these hc outside of the box, then you can see that here we are left with 1 divided by lambda 1 minus 1 divided by lambda 2. Okay, good. The next topic that we're going to discuss is black body radiation. Okay, a little bit complex topic that might confuse some people, but let me try to explain it to you in the simple language. Radiation is not something a little bit hard, something complex. In fact, in simple terms, radiation is merely spread of energy. Yeah, how energy is spread out. In fact, for example, look at this very curvy line, which is pretty good because wave, we know that light is electromagnetic wave still. So yeah, this is called dualism, light dualism, because it can behave both as a wave and a particle. The particle of nature of light was supposed by Max Planck, proved by Albert Einstein, and he got his Nobel Prize for that, not for his general theory of relativity. And wave nature of light still works because it was proven experimentally by Thomas Young and was proven mathematically by James Clerk Maxwell. Yeah. So basically, this idea still works. Wave is merely a method of radiation. Okay. Wave is a transmission of energy. Yeah. Without transmitting the thing itself. As I have told you before, if we have some wave, these individual particles of water do not have to travel like this. They do not have to travel along the wave, but instead they can share their energy. For example, this will oscillate just in its place, and then it just spreads its energy to the next particles of the water. Okay. What is about the black body? What is black body? Yeah, two parts of this idea. We have some radiation. We have some black body. What is black body? Well, it is theoretical abstraction again. It's not something real. Instead, nothing is really black. Yeah, in nature we don't have 100% black object which totally absorbs light. Well, we do have. Those are black holes. However, if we're referring to just usual materials in our daily life, then of course we don't have something black. Okay. And as I know, maybe the strongest black thing is probably 99.7% black. So, which means that it reflects some light in the form of just a very low 0.3%. Yeah, it is not that much, but still it is there. Use term to describe complete absorption. Yeah. So as I have told you, theoretical abstraction. We theoretically assume that something is something if it is black. Yeah. Because we know that white light is the mix of all colors, as I have told you before in the wave optics. But black color, it's in fact is nothing. Yes, the black body is only the absence of light, and that's it. It is not something by its nature. Nothing is there. In fact, if we have some photon, then it's light. If we don't have some photon, then of course this is our darkness. So it's not something. It is just absence of something. Okay, but by itself, it's not some natural idea. Okay. So we just assume something to be considered like a black body, and this thing doesn't have to be some black. Maybe some things might be not much of a black, but still be considered as black body. Okay, so it's just theoretically 0% transmission, 0% reflection. Of course, yeah. Transmission, we mean that, for example, when you have some lens, for example, yeah, and when light shines on it, of course it gets refracted, but when it passes through, that thing is called transmission. Yeah, this thing, letting light to get through. And black body does not let light get through, and 0% reflection because it does not reflect any light; it completely absorbs it. Okay, if we consider it in the form of the apple, well, apple can be considered somewhat of a black body. Yeah, why not? And when we shine with some light, yeah, in atomic level, we have some nucleus, we have some electrons. Yeah, of course, this is not an actual image of the atom because this is not some orbitals. Of course, we know that by Schrödinger's idea, it can be anywhere. In fact, electron must look something like this, only cloud of possibilities where it can appear. But it's not much of an important thing right now. Right now, let's concentrate on it. When we know that white light consists of all of the colors, right? But why do we see, this is our eye, yeah, this is, for example, me or you, why do we see apple as red? Well, because it absorbed all the other colors instead, apart from red. It has red color because other colors got absorbed by it, okay? But when it absorbed light, these electrons gain some energy because each of the colors are different lambdas, different frequencies. That's why they are different energies. When it absorbs some energy, right, it starts to how can I say it? Vibrate. Yeah, they start to vibrate, and they do not keep vibrating all the time. Instead, they spread it out. They radiate that energy out in the form of thermal energy. Okay, in the form of thermal energy, and that is exactly what our black body is. Okay, so I hope that it will be pretty much clear to you after I explain to you the Stefan Boltzmann law, because it is one of the topics which connect to that black body radiation. In fact, we are not going to the next topic. It is just continuation of the previous one. Stefan Boltzmann law is this kind of law. You have some power of light. Yeah, we also call it luminosity. Yeah. And it has such kind of formula, which is E, this is sigma, area, and temperature in the fourth power. Yeah, E is emissivity, coefficient of how much of a black body the thing is. So for example, if you look at here, if our E is maximum, yeah, if it is 1, then it is perfect black body. It is perfect black body. If it is exactly equals to 0, then it is perfect white body. Yeah, it does not absorb any light. Instead, it reflects it totally. And if it is between 0 and 1, then it is a gray body. Yeah, we call it gray bodies because it's something in between. Okay, because they can also reflect some of the light and absorb some of the light. Okay, okay. So what is the black body in our daily life? Water-based objects like humans can be considered black bodies. And as you can see here, emissivity of human beings is 0.97. What makes us 97% as a perfect black body? Yeah. And that is the exact reason why we can absorb some energy, absorb some heat, absorb some light's energy, and spread it out in the form of thermal energy, as it's in the black body radiation. And some minerals like aluminum and silver, yeah, they are considered almost perfect white bodies. Yeah, their emissivity is very low, 0.05, or in silver it is 0.02, even smaller. Yeah, so that's the very reason why we use aluminum in our mirrors, because they reflect light pretty good. Yeah, they reflect light. And for stronger mirrors, for example, maybe in telescopes, maybe in other places where very strong, powerful mirrors are needed, they use silver instead of aluminum. Okay, good. This is Stefan Boltzmann constant, which is 5.67 multiplied 10 to the power of -8. And then it's just a unit. Okay, A is the surface area of that thing, okay? And T is temperature. Okay, what is the surface area about? What is the temperature about? Okay, if we go a little bit lower, for example, we have some, let's say some two stars. One of them is blue, one of them is orange, for example. Well, we can see this thing a little bit later, also in Wien's displacement law, but right now let's discuss it. Let's discuss this one. Well, later, when we study Wien's displacement, we can see that temperature, well, if the thing is blue, yeah, if the star or any fire is blue, then its temperature is higher than the orange one, okay? And also star has some surface area, which is 4 pi r squared, because it's not circle, it is spherical, yeah, right? Something like this. I hope you can imagine it. Which means that its luminosity, yeah, its power of light would be very high compared to this one, because it has both things lower. It has both temperature lower and its radius is small radius. And here you can see it's a large radius. Yeah, we have two stars. One of them has large surface area. This is smaller surface area, smaller temperature, higher temperature, which means that their difference in their powers or luminosity would be very large, because the first one wins both on area and temperature in 4 times, right? In the fourth power. That's why their luminosity difference would be very high. Okay. Wien's displacement law. The formula goes like this. Lambda, well, we can write it in different form. It is lambda multiplied T equals to B. Okay. Well, but if we are being exact, this formula looks a little bit strange. B is a constant. That's why let me write it already ready like this. Lambda max, the maximum lambda, multiplied temperature of the thing equals 2.898 multiplied 10 to the power of -3, or to write it better, it's just 2.9 10 to the power of -3. Okay? Okay. The definition of Wien's displacement law goes like this. Wien's displacement law states that wavelengths at which a black body emits radiation most intensely is inversely proportional to its absolute temperature. So if we throw this temperature to there, we can see one thing very important, that lambda equals that B, which is our constant, yeah? Then lambda equals B divided by T. Okay, in simple terms, in my terms, it would be something like this. Temperature and lambda wavelengths are negatively proportional, inversely proportional, as you can see it. T and lambda. What does it mean? When we see some fire, let's say, yeah, then let's think which one of them hotter, yeah? in daily life, as being a child, we growing up think that red is the association for fire, blue is the association for water. That's why red is hot, blue is colder. But in fact, if we look at Wien's displacement law, we can see that if the temperature is high and it is inversely proportional to the lambda, to the wavelengths, then the lambda has to be short. And if the lambda is short, if the wavelength is short, then it has to be blue light, not red light. Yeah. So if we have some blue star like this, yeah, you have some star which is blue, then it has short wavelengths, but it has very high temperature, which means that this star is hotter than this star, which looks just very, very hot, right? Because we don't expect this thing to be much hot, but we definitely believe this thing to be very hot because it associates with some lava, yeah? Okay. But this thing, remember that this thing is not our sun. Instead, this is some different star because our sun is in fact white. Yes, sun is not yellow, sun is white, because if sun was yellow, then the snow at the winter would be yellow as well. Yeah, but it is not. It just happens due to scattering of light, which we are going to talk about a little bit later. Maybe not in this video. So if the light is red, then it has longer wavelengths, but we know that wavelengths and temperature are negatively proportional. That's why if you have red light, then it is in fact colder. Okay, the last thing that I want to show you is something maybe from your childhood, but it's definitely from my childhood. If you have watched Avatar: The Last Airbender, then you might remember about the final fight between Prince Zuko and his sister Azula, the Princess Azula. They had a fight, they're firebenders, and Azula was a prodigy, yeah, a very talented bender. And Zuko, in fact, was not a failure, but was not much of a talented as his sister, and his sister is probably the single character which who can bend blue light, yeah, blue fire. I'm sorry, and Zuko bends just a regular orange fire, and this looks really beautiful. But in fact, if we think that Zuko's fire is hotter just because it looks hotter, yeah, because it's orange, but in fact, it is not. As we have told right here, yeah, lambda and, well, here, yeah, temperature and wavelengths are inversely proportional. That's why orange has longer wavelengths than blue one. Its wavelength is shorter. That's why its temperature has to be smaller. This temperature has to be higher. Temperature of its blue fire has to be higher. Okay. I hope it was very clear to you. If it was not, you can write me privately, and I will try to answer for your questions as best as I can. Okay, thanks for your attention. Goodbye.